Hello, everyone, and welcome to today's class. Last week or the previous week, we introduced the concept of simple linear regression, and we said that the simple linear regression model looks like this: beta naught plus beta 1 of x plus the error term. Okay, so where here we say y is the dependent variable. So this is the dependent variable. And then x, so y is the dependent variable, and then x is the independent variable. Then beta naught and beta 1 are the regression, we sometimes call them the regression coefficients or parameters. And the regression coefficients are always unknown. They are always unknown. So if they are known, it means that our main task will be to estimate them. Our main task will be to estimate them because they are unknown. So we estimate them using the data that is available. Then we also have u here, u, which is the residual or the error term. So this part of the model here is the explained part that gives the explained variation. Let's say the explained part of the model. The explained part of the model. And then this is the part which is not explained. This is the part which is not explained by the model. Because you know, if you look at a variable, if you are trying to predict y using some variable x, in most of the cases you find that x may not be the only variable that affects, or may not be the only force, if I may call it like that, may not be the only force that is affecting y. You find that there are many other factors which are also contributing to the value of y. So those many other factors which are not captured in the model are plugged into the residual. They come into the residual. But if your model should be good, or for your model to be good, we know that whatever is plugged into the residual section should be as small as possible. So here we want to make sure that this is minimum. So for the model to be good, whatever is captured under the residual should be minimum, should be almost negligible, in such a way that if you are to look at the part that is, if you are to look at the ratio, of the explained variation and the total variation, if you are to get the total variation of y, and then this is the explained, the part that the variation in what that is explained by the model, if you take this ratio, should be as large as possible. And that means that if you take the unexplained, if you take the ratio of unexplained divided by the total variation, should be as small as possible. So you want to make sure that whatever remains here is minimum. Okay, that's why we gave the assumptions. The assumptions of the OLS, they are all revolving around the error term, the behavior of the error term. Okay, so I'll not be repeating the assumptions of the OLS because you already have them. So as I mentioned here, our objective is to estimate beta naught and beta 1. Okay, but at the same time, we want the error term to be as small as possible. Okay, so if you recall how we started last class, you start with a scatter plot like that. Okay, then you fit a line. Assume that's the line. You fit a line. So you notice that this line is fitted in such a way that if you are to take the positive residuals and the negative residuals and you sum them, if you sum the positive, or if you sum all the residuals, chances are very high that you're going to get 0, or a number which is not very different from 0. Okay, so when we say that we want to minimize this error here, we may not use actually we do not use the actual or the absolute. We do not use the absolute residuals. We do not use the simple differences between the observed value, the true value of y and the fitted value of y. Okay, so to avoid this issue of summing up to 0, we use the squared residuals. We use the squared residuals. So instead of using these vertical distances here, because those are the residuals, and we are saying that if you sum them, you are likely to get 0 in most of the cases. So to avoid working with a 0, we square them. So you square them. When you square them, you will get something like this. You square them. So once you square them, you try to minimize. You are looking for a line which minimizes the sum of those squares. Okay, so the baseline of fit is the one that minimizes, is the one that minimizes this squared sum of squares. Sorry, sum of residuals, sorry. Oh, sum of error. Okay, so that minimizes this squared sum of residuals. Sorry about that. So we're saying that the baseline of fit is the one that minimizes this squared sum of the residuals. Squared sum of the residuals. And that line here that does this job is obtained using the OLS method. Is obtained using the ordinary least squares method. Okay, where the word least here means the minimum. The minimum. But these squares here are the residual sum of squares. The residual sum of squares are the ones we are referring here to, the squares here. So when we talk about minimization, we mentioned that minimization is obtained using differentiation. Differentiation. Okay, and we started by estimating the population regression function. The estimate of the population regression function can be estimated like this: y is equal to beta naught plus beta1 x is a 1, then plus the estimate of the error. This is a population. This is an estimate, sorry, of the population regression function. Okay. Then the estimate of the sample regression function, or the fitted line, is usually given by the estimate of y is equal to beta naught estimate plus beta1 estimate of x. There's no error. Okay, so the residual is the difference between these two functions or equations. The residual is y minus y hat. Is y minus y hat. So this one minus that. And if you take the difference, what do you get? The difference is you estimate. So the residual, sometimes called the error, is given by the true value of y minus the fitted value of y. Minus the fitted value. This is the estimate. This is the true value of y. And then this is the estimated value of y. The estimated value of y is the one that is obtained using the regression line here. So using the OLS method, our objective is to minimize the sum of square of this. So you can square this. Let's start by squaring this. So if you square this, you will get this y minus y hat squared. But here our interest is the sum of square. So this is what we're calling the sum. Let me call it like this. The residual sum of squares. And as I've mentioned, the objective of the OLS method is to minimize this function. Minimize this function is the goal of OLS. Okay. So, and minimization, you just need to use differentiation. And as you know, in differentiation, if you want to obtain a maximum or minimum point, there are two conditions that must be satisfied. We have what we call the first order condition. And the first order condition here says that the first derivative is 0. So you just perform the first derivative and you equate to 0. And the second condition, second order condition, is that the second, so there are two parts of the second order condition. So we say for a maximum point, the second derivative is negative. We shall not be looking for a maximum point. We shall be looking for a minimum point. So we say for a minimum point, and this point is a turning point, because what you're calling a minimum or maximum point must be a turning point of the function in question. So for a minimum turning point, point, the second derivative is positive. Okay, it is good for you to note that the function that we are dealing with here. So I want to write this statement here in a more friendly way. So I can just say that by replacing, I can replace with this information. So I can have, I can say my summation of u squared is the same as summation of, so I'll keep the y, but now instead of having the estimate of y, I will have this. I can replace the estimate of y with this. So I'll end up with y minus beta naught estimate minus again beta1 estimate of x. Then I close brackets and say square. So this statement is just similar to this. Okay. So the best way to look at this function, you look at this, look at it as a function of beta naught and beta 1. So don't look at this as a function of y and x. Look at it as a function of beta naught and beta 1, where these guys, of course, are unknown. Okay, so that means that our differentiation, so that's our differentiation, and in this case, it will be partial differentiation. Partial differentiation will be with respect to beta naught and beta 1. So we are not differentiating this function with respect to y or x. We are differentiating this function with respect to beta naught and with respect to beta 1. And that is what we call partial differentiation. Or we shall be obtaining the partial derivatives of this function. So we said that for convenience, we can let this guy here to be something simple like an s. We can just say that s, where our s here represents the sum of square due to errors, is the same as, then I keep the right hand side, y minus like that, minus beta 1 of x. So we have that. So that now we look for partial derivative. That's how we denote partial derivatives of S with respect to the first variable in this function. It's beta naught. So you differentiate this with respect to beta naught. That's the first partial derivative. So this is a first order condition now. So you equate whatever you get to 0. Okay, and then you also do a partial derivative of S with respect to beta 1, and then you equate to 0. So this is what amounts to first order conditions. First order conditions. And we say that if you perform the partial derivatives very well, you will end up, the result here, the result of this process here, the result of first order condition is what you call the normal equations. I suspect you are very much familiar with normal equations, where the first normal equation will look like this: summation of yi is equal to n beta naught plus beta 1 summation of x. So let me remove these denotations to keep it simple. So like that. That's our first normal equation. It's only that in the notes we had all these guys on the left hand side. We had everyone. I think we reported something like this, which is the same. Summation of y minus n beta naught minus beta 1 summation of x is equal to 0. These two statements are exactly the same. They're exactly the same. And then the second normal equation, I just want to write them in a familiar way, the way that you have been used to. Then the second normal equation, so this one is coming from the first derivative. It's coming from here. And when you perform this, you will get a summation of xy is equal to beta naught summation of x plus beta 1 summation of x squared. So these are what we call the normal equations. If you have if you are running a simple linear regression, then you have two normal equations. If you want to use the OLS method, you have two normal equations. And by extension, when you go to the multiple linear regression, if you have 3 variables, then you'll end up with 3 normal equations, and so on and so forth. So if you have 10 variables, that is 1 dependent variable and 9 independent variables, you will end up with 10 normal equations, and so on and so forth. Okay, then we confirmed that if you perform a second derivative, that is using the second order conditions, we performed that the partial derivative, the second partial derivative of S with respect to beta naught was a positive number. We saw that you will get a positive value. And the same case, if you perform the second partial derivative of S with respect to beta 1, you'll also get a positive number. So that confirms. So this confirms that S is minimum. So if you get this, it means that your S is actually minimum. So that means you have minimized. That means we have minimized the residual sum of squares. We have minimized that. So then, so the next thing is just to make. Next is to make beta naught and beta 1. These are estimates. The subject of the formula. The subject in the above. Using the above normal equations. Using the above normal equations. So once you confirm that your S is actually minimum, now you can make beta naught and beta 1 the subject of the formula. And we saw that if you play around with the values, there's a video that I shared which shows how the algebra that is involved in that manipulation. You see that the value of beta 1 estimate is equal to the summation of x minus x bar, y minus y bar, then divided by summation of x minus, I'm just trying to keep the notation quite simple, like that. Okay, so that's the estimate of beta 1. And then beta naught estimate is y bar minus beta 1 estimate, then we have x bar. Okay, then we noted that this expression here can be written in different formats by noting that we note that the summation of x minus x bar y minus y bar is equivalent to, so this is exactly the same as the summation of x multiplied by y minus n multiplied by x bar y bar. Okay, so this simplifies the formula above there. Then if you have the denominator there, so number 2 is that if you have this can be rewritten as summation of x squared minus n x bar squared. Remember here it is only the x bar which is squared. Yeah, that should be clear like that. Okay, so you can use these expressions to make your work a little bit easier when doing the computations. Okay, then the value of beta 1 can be expressed in terms of covariance and variance. So we said that also, sorry, not also, it's part of the note. We said that beta 1 estimate can also be rewritten as the covariance of x and y divided by the variance of x, divided by the variance of x, where we know that covariance of, usually we write it in short like this, covariance of x and y is given by this arithmetic mean, summation of x minus x bar y minus y bar divided by, in most of the cases we use divide by n minus 1, divide by n minus 1, divide by n minus 1. So it means that you can write that covariance in this format, summation of xy minus n x bar y bar divided by n minus 1. So this is exactly the same thing. So you can have it in that format. Then the variance, we can write it like this, variance of x. And remember, all these are estimates. So usually we have, it's only that it will look a little bit like that. So these are estimates. Estimates of variance and covariance. So we know that the variance by definition is given by summation of x, the summation of x minus x bar squared divided by n minus 1. Okay, so which we can write using this expression here as summation of x squared minus n x bar squared divided by n minus 1. So you can write this term beta 1 in form of variance and covariance in that format. So so we can also, in more symbols, we can say this is the same as s of x y divided by s of x squared. So this is a covariance of x and y. It's the same thing. Then this is a variance of x. So it's good for you to be familiar with the different ways in which beta 1 can be expressed. So this symbol here, s x y, means the covariance of x and y. And then s squared of x, this is a variance, because we know that s squared is variance, and then s is the standard deviation. But when you talk about covariance, you just use x, then you have the variables in question. You don't have squared here. Covariance is just denoted like that. Okay. Then note number 4 is that beta 1 can also be expressed as in form of correlation. So you can have beta 1 estimate as s of y divided by S of x, then you have R of x, y, R of x, y. Okay, where R of x, y is the correlation coefficient. Is the correlation coefficient. And how do you get the correlation coefficient? This is the same as the covariance of xy divided by the standard deviation of x multiplied by standard deviation of y. Oh, sorry, let me write in full. The covariance of that divided by standard deviation of x multiplied by standard deviation of y. So that's what we have. So sometimes you write this one as s xy divided by s of x of y, like that. So you know, I think I showed you last time that it's just a way of playing around with this expression here. If you play around with this expression, you will end up with this. You'll end up with this. You'll end up with this. And then s of y is the standard deviation of variable y, and then s of x is the standard deviation of x. Okay, right. Then what else did we mention last time? So we had some example. Where the objective was to find the values of beta 0 and beta 1 using some of these formulae. And we use some data that is given in the textbook. The data is called wages.raw. And did I share with you that kind of data? So let me display the data, then we can obtain the statistics. Then from there, we can also calculate the values of beta 0 and beta 1. So let's consider this data, the wage data. So we are going to use Excel to obtain the basic statistics. And as we said last time, when you click on the data tab here on your Excel, you should be able to see this data analysis tool pack, this one. So once you've installed it, you just need to come here, you click here. I want to obtain, there are several things that you can get from here, but let's get the descriptive statistics from here. So we say, okay. So we want descriptive statistics of, let me delete this. So I'm going to select the 2 columns of my data. So those are my 2 columns of the data. Then they are grouped by columns, so I don't change anything there. Then I can check here. This one is usually unchecked, so I can check this part so that I get the descriptive statistics, things like the mean, the median, the mode, and so on and so forth. So I just say, okay, my output will go to a new worksheet. So you say, okay, there. And here is the information. So column one in our data was what? Column 1 in our data is wage, and the other one is education. So this is wage, and then this is education. So these are the statistics corresponding to the variable called education. So we have the mean value, we have the standard error, the median and the mode, we have the standard deviation, the variance, okay, then we have the kurtosis, skewness, and so on and so forth, okay, the sum and the count. These are the number of observations, So this is the information. I think in the notes I've added covariance. I've added covariance between these 2 variables. So but that's the procedure of getting those statistics. So if you go back to the notes, you notice that we are given this information. So we want to obtain beta naught. Of course, we were able to do it using the software, and we got that these are the answers. So we want to replicate these results using this information here. So I want us to try that and see if you're going to get these values, beta naught and beta 1. Okay. So let's find the solution. And we start by getting the value of beta 1. So beta 1 estimate is given by, from the information given, we can use covariance, which is SXY divided by A squared of X, which is given by what? Someone can unmute themselves and give us the values. So which values are we using here?
We already have covariance, which is 4.15.
0.864. Then divide that by
variance of X.
2.76.
2.769
022 squared.
Squared, yes.
Squared, because
squared.
Because what we have there is S of X.
Yes.
So if you want to get S squared of X, you just take S of X times S of X, which is the same as S of X squared. So you square. This is the standard deviation. So once you square it, you get the variance. So this gives us what value?
0.541.
135.
Point what?
0.4135. 35.
So let's start again.
0.541.
541. Thank you.
Yes.
Then let's get Roman 2. That is beta naught estimate, which will be given by So if that noise is coming from your side, please mute yourself. So sorry about that. So we have beta naught estimate is equal to Are you there?
Yes, we are, Malim.
Yes. So so beta naught estimate is given by
Y minus estimate of beta naught 1 X bar.
X bar, and we already have all this information. So where Y bar is equal to the mean of Y, 5.89 something, so 5.89 something. Then we already have now the value of or the estimate of beta 1, 0.541 multiplied by X bar, and X bar in this case is 12.56 something, 12.5686. So use the real values. Don't round off too early so that you get the correct answer. When you do that correctly, what value do you get?
Just hold on, Malim kidogo.
I think. Hello, teacher.
Yes. So you're saying the answer is minus 0.?
Minus 0.9048. Or
let's say these are like that.
Yeah.
So those are the values of beta naught and beta 1. And also you can calculate them manually if you're given the sample statistics. Then you can also obtain these values using Excel or using any other statistical software as we saw last time. So as you saw, the procedure is quite simple. You just need to come to your data here. You come to the data tab, you go to data analysis, regression, you choose regression, then you input the range of your y variable, and our y variable is which one? Wedge, isn't it? Wedge is our y variable. So you put the range, that is you capture all the cells that capture that. So you select all that, select all those cells, and you come here, do the same. So I select all these. You select all that. Then here you can leave it the way it is. So you may want to look at the residuals if you're interested, maybe the residual plots. But now you can just say okay. Then you'll get your output here. There are 3 tables there. I'm going to skip the first and the second. So the last table is the one that shows us the numbers, the estimates that you have just obtained there. So this is your beta naught estimate. That's your estimate of beta naught, and this is your estimate of beta 1. So using Excel or any other statistical software, you just need a few seconds, and then you have the values like that. You have the values like that. Okay, and these are the residuals, the residual plots. If you are to plot the errors, that's what you'll get. Now, this is what you check against the assumptions that we made, especially assumption number 5. But we'll be looking at that a little bit later. Then here, down here, there is some information about this is the predicted y. So this is your y hat. This is your y hat. This is your y hat, is what you're calling the predicted y. Okay. Then your true y, the original data here, this is your y. This is your y. This is your y. And then what we have here is your y hat. This is your y hat. So the residual here is the difference between the y and the y hat. So these are the residuals or the errors. These are the errors. And remember we said that we want to make the errors as small as possible. And one of the property of the OLS is that the residuals will always sum to 0. So I'm just highlighting the residuals. I'm just highlighting the residuals. Then if you check the sum, let me do it here. If you check, if you say the sum of, if you pick the sum of all these, you pick the residuals like that, then you get the sum. It's a very small number. It is times e raised to the power minus 12. So this is I want to round it off. I can say round this to round this value here to, let's say, 3 decimal places, so that we see exactly what is the number we're talking about. If you round off to 3 decimal places, the number will be 0. So that's one property of that OLS, that line of best fit, to make sure that the residuals will sum to 0. And that explains why, instead of using the residuals to estimate the values of beta naught and beta 1, we use the squared residuals. We use the squared residuals. Okay. Now let's move on. So if there's no question about the beta naught and beta 1 estimates, let's look at some properties of the OLS regression line. And the first property is something that we have seen practically, is that the sum and the average and the mean, the sum and the mean of the OLS residuals is 0. That is, if you take sum of you estimate, you should get 0 if your I runs from 1 all the way to n. I think we've seen that. If you check here, we saw that if you take, these are the residuals. If you sum these residuals, we saw that the sum of these residuals is very close to 0. Theoretically equal to 0, but practically it may not be 0, but should be should be very small, very, very small. So you saw in our case, this is the value we got when you sum the errors, which after rounding off, we saw this is equal to, if you round this value, let's say to 3 or 4, 5 decimal places, you will get 0. So that's one of the property of the OLS, that when you sum the residues, you will always get 0. Okay, the OLS residues will always sum to 0. Then the second property is that by construction, the sample covariance between the OLS residues and the regressor is 0. The regressor here is the independent variable, or X in our case. Okay, so we're saying the covariance is equal to 0. When the covariance is 0, it means that the correlation is also equal to 0, because we know that correlation of between X and Y is given by the covariance between X and Y divided by the standard deviation of X multiplied by standard deviation of Y. So if the covariance is 0, if the numerator is 0, it doesn't matter whatever is here, then the correlation will also be equal to 0. Okay, so that is, if you take covariance of X and U, this one should be equal to, which is also equal to, given by these, X, U. I should be putting the Xi's like that. Then like that. Then for I starting from 1 all the way to n, this one should always be equal to 0. This one should always be equal to 0. Okay. So, and we're saying that this one means that the correlation R will also be equal to 0. Correlation coefficient will be equal to 0. I think we have seen that the correlation between X and the residuals in our example above is equal to 0. Okay. So now I want us to look at something very closely related to what we have been discussing. So this is the partitioning. Partitioning of the sum of squares. The partitioning of the sum of squares. So we say that we start by saying that from the normal equation. So from the normal equation, that y bar is equal to, from the first normal equation, we can make y bar the subject of the formula, and you observe that y bar is equal to beta0 estimate plus beta1 estimate x bar. We can have it like that. Then we can show that the total sum of squares, which is denoted by that SST, total sum of squares, will be given by SST is equal to summation of, if you take yi minus y bar, then squares. Of course, we are summing from I is equal to 1. We are summing for all the individuals in the sample. So the total sum of squares is given by this. You take, this is the original data. This is the data observed, or observed data. And this is the mean value. So if you go back to our, illustration here, this is what we are calling, when you're here, this is our y. This is our y. This is our y variable. Then we are given y bar. we know the mean of y, and the mean of y was given here. So this was our y. So the mean of y is given by this value. The mean of y is this number here. So when talk about the sum of square total, the sum of square total, this will be given by, if you come here, you say, so if you say y minus, let's say y bar, this will be given by, you say equals, then you say this minus this number here. The mean of y is how much? The mean of y is 5.89 something. 5.896103. Okay, so that is y minus y bar. So you copy all the values all the way to the last column. Then we need to have y minus y bar, but now we need to have it squared. So let me just call it SST, because let me call it sum of squares, like that. So this will be, you take this value here, then you square it. So I've squared the differences. Then I go down there, this is SST. You go down there and then you sum. If you come down here and then you sum, so if you say here sum, then I want to sum everything that is in, let me do this. I think it is easier to do this. You come here and say auto sum, yeah, like that. So this is the total sum of squares. So this is our SST. This number here, this number here is your total sum of squares. So this is just sum of squares. Sum of squares. So this is your value of SST. This number here. Okay. Then we also have another type of variation. I will show you how we are going to use them later on. Then apart from the SST, we also have number 2, our second point is the explained sum of squares, which is we denote using SSE. Okay, and SSE is defined as, you take summation of y hat, we're using y hat minus y bar squared. So we're 1 all the way to n. So you take the estimated, this is the estimated or the fitted value of y. The estimated or the predicted value of y. Then of course this is the mean of y. Mean of y. I think I said that here. Yes, mean of y. So that gives you what we call the explained sum of squares. Remember, we said that if you look at this model, y is equal to beta naught plus beta 1 of x plus u. We said that this is the explained. This is the part that explains the variation in y. And this is the unexplained, the residual. Okay. Then finally, we have what we call the residual sum of squares, which we shall denote here as SS residuals there. And the residual sum of squares is given by SSR is equal to the summation of yi minus y hat squared. So this is the original data. This is the observed data. And then this is the predicted the difference between the observed value and the true value and the predicted value. Okay, so the sum of squares can be partitioned into those three ways: the total sum of squares, the residual sum of squares, and the explained sum of squares. So when we go back to our, if you go back to our Excel here, if you go back to our Excel here, if you want to get the explained sum of squares, if you want to get the explained sum of squares, let me just call it ESE or SSE, the explained sum of squares, you need to take your y hat. Do I have it here? I need to bring my y hat here. So let me bring my, this is you, insert here. So let me bring my predicted values of y. Luckily, I have them. Predicted values of y were given here. So these are the predicted y. So I want to copy all these values. You copy these values, you bring them here. So this is y hat. Huh? Let me call it like that for simplicity. So now I have my y, I have my y hat, and then I have my, I know my y bar, so I can just use it from wherever it is. Huh? So my explained sum of squares will be given by, you take your value of y hat, which is this value here, y hat, you minus the value of y bar, and we got our y bar was 5.8 something, 5.896103. So you have that, huh? But I need to have it squared. I need to have it squared. So I'm going to square it at this point. I'm going to have it squared like this, raised to power 2. So that now, I just copy the formula down. Then I want to get the sum. So sorry, this one is SS total. Then here I need the auto sum here, like that. So this one is the explained sum of squares. So the model, so this is the total variation in y, and the model is able to explain this amount of variation. The model is able to explain this amount of variation. Then we also have now the residual, and the residual sum of squares. I think I already have it. Huh? The residual sum of squares. So let me have it here, SSR residual. The residual sum of squares will be given by, or is given by, you take your value of y, that is your original data, you minus the predicted value, you minus the predicted value of y. That gives you the residual, that's the residual. Eh? Then I need to have it squared. Alternatively, do I have the residuals here? I could have taken this value here just before I square it. As you can see, this value here is the same as this value. So I could have taken this column called u, and then I just square it because these values are the same. But I'll not do that. I just come here and say, I put bracket there. Then I raise to power 2. Raised to power 2. So I'm squaring my residuals like that. It's the same as squaring this column. Then I drag the formula down. So, and now I need the sum down there. I need to sum. So I need to sum these values. So I need to come here and say auto sum. Okay, so you have that. So this is the unexplained part of the model. This is unexplained variation. So this is unexplained variation. This is the explained variation. Okay, so and then we have this here is the total variation. So from basic algebra, I expect that if I take the explained variation plus the unexplained variation, I should get the total variation. So I'm saying if I take this plus that, I can just do it here, is equal to, if I take this plus this, I expect to get 7160.41. You'll get that. It's exactly the same. Exactly the same. Okay, so you find that this number is exactly equal to this. So you need to note that total variation, so we can say that total variation is equal to the explained variation plus the unexplained variation. Or in short, we can say that the total sum of squares is equal to the explained sum of squares plus the residual sum of squares. That's what I want us to capture in our notes here. So it can be shown that, it can be shown that if you take SST, this is the same as SSE explained plus SS residual. That is total sum of squares is equal to the explained sum of squares plus the residual sum of squares. Then using the formulas above, using these kind of formulas, we can say that the summation of y minus y bar, you can have that, squared is equal to the summation of y hat minus y bar squared, like that, yeah. Then plus you have summation of yi minus y hat, like that. So this is the residual. This is the meaning of these are residual. This is explained variation. This is a total variation. So it can be shown that, but we don't need that kind of proof. Okay. But now there's some caution somewhere, or some alert that I want to raise, that in some textbooks or some others use SSE to mean the error sum of squares. Please note that our SSE here means the explained, not the error. So this is the explained. This is the error. So if we were to use explained and error, I would have it like that. Okay. Instead of what we have used here. So let me not put this part. And then they also use SSR to mean the residual. So the regression sum of squares, which is the same as the explained, which is the same as the explained sum of squares. So that's just a caution that in some textbooks you might find that the symbols that are these two symbols mean different things. In our case, this is not what we mean. We are using, in our case, SSE. In our case, SSE is the explained sum of squares, is the regression sum of squares. So sometimes somebody can get confused. So, but you just need to be aware. And then when you talk about SR, in our case, this is the residual sum of squares. So you see all of them have an R, but we choose to use R for residuals. We choose to use R for residuals, and we use E for the explained variation. So you need to be careful about that. Huh? You need to be careful about that. Okay, any questions so far? So I want us to look at the R squared, which is one of the statistics that is obtained or very important in regression analysis. The R squared is also known as the coefficient of determination, and it simply gives us the ratio between the explained variation or the explained sum of squares and the total sum of squares. Okay, so if the model is fitting very well into the given data, then we expect that R squared should be very close to 1, or should be as large as possible. And you notice that R squared, because we're saying that is a ratio between the explained. For instance, if I were to go back to R, sorry, not to R, to our data set here, we're saying that R squared is a ratio between the explained variation and the total variation. Okay, and there's no way explained variation can be larger than total variation. So so this will be a fraction between, it will be a decimal value between 0 and 1. So if you take, for instance, here, you take this number here, divide by this number. Basically, this is what we are calling R squared, that ratio. It gives you the percentage. You can convert this into percentage, which will be the same as 16.around 5. So that means that the model that we are dealing with here explains around 16.5% of the variation in the Y variable, only 16.5%. So that means the remaining around 84% or around 83% is not explained by this model. So that is captured under this part here. So the unexplained variation will be 1 minus R squared. So let's note that this involves the coefficient of determination. This involves attempting to answer the following questions. If you want to answer the following questions, we use R squared. Number one, how good a job does your sample regression function do? How good is your regression model? Okay, or how good a job does your regression model do? The number two, does the regression function explain a great deal of the variation of Y or not very much? So does your model explain a great deal of the variation of Y? The variation of Y is what we are calling the total variation, or not? So if you want to answer those questions, you use the coefficient of determination, or R squared, which is defined as, so to answer those two questions, you use the coefficient of determination, which is defined as R squared, capital R squared, which is given by the explained sum of squares divided by the total sum of squares. So which is the same as SSE divided by SST divided by SST. Okay, which we are, because we know that SST is equal to SSE plus SSR. We know that. So this means that SSE is the same as SST minus SS residual. We know that. So we can replace the numerator here with this term here. So that means that we have this as SST minus SSR divided by SST. So we can split the numerator into this format. So we have SST over SST minus SSR residual divided by SST. So we know this is the same as 1 minus SSR over SST. So that is the explained variation. I mean, that is the, this is the, so R squared is the amount of variation in Y that is explained by the model. And this is usually reported as a percentage. Okay, so usually R squared is a number between 0 and 1. So R squared is a number between 0 and 1. 0 and 1. So when your R squared is equal to 1, it means that you have a perfect fit. If your R squared is equal to 1, it means you have a perfect fit where the sum of squares due to the residual is 0. When this guy is 0 here, if the sum of squares due to the residuals is 0, it means that your R squared will be equal to 1. That's a perfect fit. It is very unlikely to occur. So in most of the cases, you find that it is in between 0 and 1. That also means that if your SSR is equal to the total sum of squares, then your R squared will be equal to 0. That means that your model is explaining 0 variation in the value of Y. That means you have a very poor, you have the worst fit, if I were to say that. Okay. So let's note that the positive square root of R squared, if you take square root of that, is called the multiple correlation. Is called the multiple correlation, and which is denoted by, we use letter R. So we're saying that if you take the square root, you'll get, you know that you're likely to get plus or minus R. So we're saying the positive value, the positive square root is what we're calling multiple correlation. Okay. When you say that in the case of simple linear regression, R squared is the same as small letter r squared. That is the coefficient of determination. The coefficient of determination is equal to the square of the correlation coefficient. Is equal to the square of the correlation coefficient. Maybe if I said xy, this is a correlation coefficient. So once you take it, you square, you will get the coefficient of determination. But this cannot be generalized. This statement here cannot be generalized to multiple regression. You cannot generalize this statement here to the case of multiple regression. So that statement is only true in the case of simple regression. Okay, so I want us to go back to the example above, the example that we looked at a little bit earlier on, and obtain, so example, so using the information given above there, compute R squared. So we're using this information here. Using this information, So using this information, let's obtain the coefficient of determination. And I think I've shown you that if you compute the coefficient of determination, you should get this value, 0.164 something. Okay, so I want us to obtain that value manually using this information here. Okay, so in this case, the hint is you just need to obtain R. That is a correlation coefficient. And we know that correlation coefficient R is given by covariance of xy divided by standard deviation of x multiplied by standard deviation of y. So once you know that, you are good to go, because all this information is found here. So let me give you 1 or 2 minutes to finish that. So as you've mentioned, in the case of simple linear regression, R squared, capital R squared, is equal to the small r squared, where the small r squared is the correlation coefficient. And correlation coefficient is given by the covariance of x and y divided by the standard deviation of x multiplied by standard deviation of y. So this is the same as s of xy divided by s of x, s of y. So the covariance as given above is 4.15864. Then we have the standard deviation of x is 2.769, and the standard deviation of y is 3.693 something, 3.693 etc. So let's simplify this. What is the value of R that we get from here? So the value of R is 0. You're saying 0.4 what?
405. 05.
05. So that's your R.
Yeah.
So our R, capital R squared, is the same as small letter r squared. So we take that value, we square it. So 0.405 etc times 0.405. So our coefficient of determination will be equal to, if you square that value, what do you get?
0.164.
64. Give me 4 decimal places.
1.647.
Thank you. So 47. So which usually we report as 16.47%. We prefer to report it in that format, percentage, yeah? Because it is easier to explain a percentage than the decimals there. So so what does that mean? So this means that so we say that R squared, which is 16.47%, tells us that the model explains 16.47% of the variation in Y. So 16.47% of the variation in Y is explained by that model. It is explained by this model. Remember, the model is estimate of Y. What were the values of beta naught and beta 1? Minus 0.905 plus 0.541x. So this model here explains 16.47% of the variation in Y. So that means that the remaining percentage is explained by other factors which are not captured in the model. Okay, so that means the factors that are captured in the residual. So thus the difference is 83.5% of the variation in Y, of the variation in y, y is the hourly wage, is explained by other factors, not accounted by the model. Okay, which is a very high percentage. That is not explained by the model. Okay, 83.5. So there are so many other factors which have not been captured in the model, which are explaining the variation in y, or the hourly wage in our case. Okay. So you will notice that one of the limitations of the coefficient of determination, or R squared, is that it increases as you increase the number of variables in your model. And it doesn't matter whether the variables that you are adding in your model are significant or not. Your value of R squared will always grow. So sometimes it may be exaggerated. The value of R squared reported may be exaggerated. So that means that not every large value of R squared means something good for the model. You might find that it is just because we have put so many variables in the model. So to take care of that limitation, or the effect of the number of variables, we use a related coefficient known as the adjusted R squared. And the adjusted R squared is denoted by that, and is defined as 1 minus n minus 2, then n minus 1. Then you take that one, multiply by 1 minus R squared. So the adjusted R squared is given by that. So we may not want to go to the details of how it is derived, but we use the adjusted R squared to take care of that effect of increase in n, increase in the number of observations. Okay, so this one is not very much affected by the increase in number of variables, so it's more realistic than the R squared. So when you check the output here, you notice that there's also adjusted R square, the adjusted R square, which in this case doesn't seem to be very different from R square, because of course we do not have so many variables in our model. So they are very close when you have very few variables. Okay, so you just need to obtain your value of R squared the way using the formula that we have seen up there. Then now you adjust it using this new formula there. Okay, so you can compute, you can use the previous example to compute the adjusted R squared, and you know the answer that you expect to get is, so your answer should be 0.163, and so on and so forth. Okay, so next I want us to look at how to deal with non-linearities. So dealing with non-linearities. So we have just seen that R squared and the adjusted R squared, they tell us how good the fit is. And you notice that sometimes you may find that the model is explaining a very small proportion of the variation in Y. So one of the reasons is you might find that you fitted the wrong model. For instance, if you might be having a scatter plot that looks like this. You might have if you do a scatter plot here, you might have Y and X there. Then you have your points looking like that. So you notice that the kind of relationship here is not linear. So if you force a straight line using OLS, you'll find that your model will not be fitting well, and possibly your R squared will be quite small. But you notice that if you perform some transformations on the values of X, on the variable X and Y, you might end up having let's say, some X star, which is a transformed value of X, and maybe it's your Y star. So if you plot now, you might find that now it is more linear. It may not be perfectly linear, but you find that it is to a very great extent linear. So that when you fit a straight line, it gives you a better fit. So if you suspect that your R squared is small because you have fitted a bad fit, you may start by transforming the variables. And one of the most widely used kind of transformation in for economic variables is the logarithm transformation. And there are various ways of transforming variables using the log transform. So I've given here 4 types of models that you can get from that transformation. So the first one, we have a level model where you do not transform the variables. You fit the variables like the way we did in the previous example. And here we say that the interpretation of beta1 is that for every unit change in the value of x, for every unit increase in the value of x, then the change in y is equal to the value of beta naught. So for instance, in our example, we got that your y estimate is equal to, what was the values? What were the values of beta naught and beta 1? What were the values of beta naught and beta 1? We had minus 0.905 plus 0.541x. So this is our value of beta 1 estimate, of course. So this means that for every unit change, for every unit increase in x, then the value of y in this case increases by 0.541. So that's just a straightforward interpretation. For every unit increase in x, then the change in y is given by this value. The change in y is given by that value.